So there's one problem about boring a hole through the middle of the earth, which you know, it's a normal thing to do, all the way through the earth. And then you drop something down, and it's about setting up an equation, a differential equation that you could solve to get it to motion. Now, very quickly, why do things fall? What do they actually fall towards? The center. So very often in physics, we'll reduce mass to a single infinitesimal point. All the mass is right there. We don't actually physically do it, or we make little black holes. And so that is attracting whatever the mass is that I'm talking about. So if I have a satellite, we assume that the entire mass of Earth is here, so it's all about the radius away from that center of mass. So what's weird is if you let it drop into the Earth, now there's some mass like behind me, correct? Do you guys know that if you stand in a mountain range, in a valley, in a mountain range, you weigh less? Of course, weight isn't mass. Weight is just your apparent force that you're exerting on the ground, because some of the mountain is pulling you up, right? You guys kind of with me. So this problem is pretty freaky on the surface. Yes, it's really weird to think about. The one thing I don't think they give you, which is stupid important, is Newton's gravitational force formula. And it is possible some of you guys know it, but it's not fair if you don't. So I think it's 24. I could look it up, but I'm lazy. So the force, and I think the book, if it's in the book somewhere, I think they put a K instead of a G, but it should be the gravitational constant. Let me put this down and see if anybody, that strikes a chord with anybody. So this is the force between two bodies due to gravity, right? So for example, most often if I drop an apple towards the earth, it's not surprisingly make the earth's mass this big ass M, because the earth's mass is big. The really weird thing about this is when you drop something towards the earth and the apple both exert the exact same force on each other. Let me say this again, because that normally freaks people out. If I drop the pen towards the earth, the pen exerted the exact same force on the earth as the earth does on the pen. Is everybody cool with that? Yes. Now, this is not physics class, but forces, mass, times acceleration. When I divide by mass, I get acceleration. If I divide by the mass of the pen, that's why it moves. If I divide by the mass of the freaking earth, this is basically zero. So that's why the earth is like, plus there's people on the other side of the earth that are dropping shit too. So they kind of like counterbalance. You guys sort of with me? You guys sort of with me? That is really weird. Let me make the earth move up a little bit. There, I made the earth move up. Okay. Sorry. I miss teaching physics, but so this is the key thing. I'm not saying this is going to make it easy. I am saying it's going to make it possible to do that problem. They also give you a big hint in the problem about when you are on the surface of the earth, the entire Earth's mass is taken into account. So I bore a hole in the earth and I drop this. Once I'm in here, it's just the mass of the sphere of the smaller radius that actually is taken into account. So just this mass is pulling me down. That is not immediately obvious. But that's the part of the problem that really makes it a lot easier than it could have been. It's just going, oh yeah, it's just that. Because what should happen at the center? Where is it going to experience no force? Well, I just basically gave away. At the center, it doesn't have equal mass above it as it does below it. And what's the radius of the circle from the center of the earth when I'm there? Zero. So effectively, there's no mass acting on me here. But that is the point where I'm going to be, what's the velocity at this point? Before that point, I'm getting pulled down, correct? Right at that point, nothing. So that is the fastest I'm going, because once I am past that point, there's more mass behind me, slowing me down. So theoretically, majorly theoretically, if we did this and I dropped something, it would just oscillate. All right, that's way further than you have to go for that problem. I'm sorry. That is probably the freakiest problem. in that section. Before I get into a couple things from 1-3, any questions from homework stuff? Is Dominic here? Hey, I got your homework. All right. By the way, before I forget, WebAssign is not an immediate thing I think of. I make it optional and then I sort of forget about it. So if you guys are in WebAssign and I kind of forgot to put the homework up, remind me. So I'm going to try to stay ahead a little bit. I think at the moment I've only got through chapter 2 up, so you can definitely get ahead. If you make a few mistakes on the written paper, I might give you full credit. Same thing with the WebAssign. Your homework grade will not be the grade you see in WebAssign. If you miss a few problems, you'll have less than 100%. For me, I'll give it full credit if those problems weren't like really important. Does it make sense? Like some major concept. You guys all with me? So I try to make the homework kind of similar in how I look at it. Okay. If you ever have a question from WebAssign, there's an Ask Your Instructor button. If I don't get back to you, just email me. Again, I don't go into WebAssign too often, I'm sorry. But, and for some reason it just won't, I try to set it to email me and it won't. It's kind of, it doesn't like me. It probably knows I don't like it, so. I don't blame it. All right, so no questions so far? Okay. Couple things from 1-3. Oh yeah, I'll do that next. So real quick, one of the very most basic differential equations, it's one of those that almost you wouldn't call a differential equation, it's like a 180 level thing, is how population grows. What would the most immediate impact, what variable would most immediately impact how quickly a population grows? The amount that's already there, right? So the change in population over time is, at its most basic, directly proportional to the amount that's there already. Now, that is way oversimplified, right? Are you guys kind of with me? Because then you also have like, well, is there rampant disease or not? Is there other competing factors, whatever? So that can kind of, that sometimes is captured by this, but not necessarily, right? You guys kind of with me? So you're going to see problems like this. One of the problems in the homework is you adjusting this a little bit. Most of the 1-3 homework is go back to the section, look at where they talked about it. How do I adjust it? How do I adjust it? How do I adjust it for certain situations? Again, you're not solving any of them, which again, very frustrating. I'm sorry. It's just the way chapter 1 is. Okay. How we doing? Today we're going to get to solve some shit. Oh, yay. Okay. All right. What was the other thing I want to talk about? Oh, here's a nifty one. Mass times acceleration. So if I just drop something, the force is provided by the weight of that, right? So mg is the weight. G, real quick, and again, you don't have to know physics to take this class. Anybody know what G is? Yeah, the gravitational acceleration. Yeah. Negative 9.8 meters per second squared, so the right units. Yes. Not our stupid American units. Okay. Based on the size of the foot of the King of England. What the shit? Sorry. So here's the one nifty thing. When you take physics, when you take baby physics, you have stuff like massless, frictionless ropes. And one of my instructors would always say, where do you buy that? So why do you do that? So you can kind of just focus on the idea without bringing too many other things in. If I drop something, so for example, y'all know this. You should all know. If I'm in a vacuum and I drop a hammer and a piece of paper, which one's going to hit the ground first? Same time, because they both experience the same acceleration. Why do they not hit the ground at the same time on the Earth?
Air resistance.
Air resistance, I love it. So won't this be diminished if I have air resistance? And here's the idea. The faster we're going, the stronger the resistance gets. So there's this idea of like if you drop an ant from the Empire State Building, it'll survive when it hits because it's got a lower terminal velocity. Whereas if you're human, you're pretty sure. All right. So here's what's interesting is it's proportional to the velocity. Now, real quick. Velocity is how related to position. Velocity is the what of position, derivative. So ds dt, is that cool? Acceleration is how related to second derivative. Isn't that a freaking, what kind of differential equation is that? Second order, linear, ODE. And where'd it come from? Real freaking life. Are there more variables than that affect something falling? Shit, yeah. Right? You guys kind of with me? There's a whole field called perturbation theory, which is where you solve the simplest thing and then you perturb the answer by introducing other variables. It's really stupid cool. So you don't have to solve from the beginning, know all variables. You just add shit in as you learn it. And just perturb, I love the idea. You perturb the original, what are you doing? Putting more shit in you. Oh, shit. Maybe. Anyway, don't worry about it. I'm sorry. You don't have to worry about that for this class. Okay. Okay. That's all I want to say, I think, about 1-3, if nobody has specific questions. I do want to do one thing related to the existence and uniqueness theorem that we talked about last time. Can somebody tell me what the heart of that is? What are the two things I need to check if I'm given a differential equation like this, just to make it nice and easy? What two things do I have to check? Yeah, is f of xy continuous on some interval?
And then the derivative is continuous.
And is, what about, be careful, what kind of derivative? Partial. I don't know why I do that still. Partial of f with respect to y, continuous, yeah, is that continuous on? Now when I say some interval, it's got to include any initial condition. So some interval around that initial condition. Are you guys kind of with me? You can boil that down to just that. Two things you check. If it passes both of those things, right? If it passes both of these things, what do I know for sure? A solution exists and it is unique. If it doesn't pass either one or both, what does that tell me? Any damn thing could happen. It could have a unique solution. It totally could. It could have 80 solutions. It could have no solution. You guys with me? So many theorems are like this. If it does this, you know this. If it doesn't do these, I don't know. So many theorems are like that, right? Which makes sense. Something related to necessary and sufficient. So if you don't have them, then it's like, I don't know, anything could happen. Okay, maybe. So here's a example, like a concrete example for once. Dear God, Jeff, I hate this thing. Here. Oh my God. So here's a little differential equation. This is kind of nifty. Okay. Is that linear? Just as a side note. One of the first things we're going to learn how to solve is a situation where even if it's not linear, it's actually very possible to be stupid easy. All right, so we'll see that later today. So I can rewrite this like this if I wanted to, right? Now the solution to this, real quick, let's do this. Let's freaking solve this damn thing. And I'll even tell you what this is called. Let me just tell you what this is called. I might have said this already. This is what's called a separable differential equation. What the hell would that mean? Separable. Can you put all the y stuff on one side?
Yes.
Can you put all the x stuff on the other side?
Yes.
Separable. Why would that be good? To be able to, how would I do that? What would I do?
Multiply dx and divide y.
Yeah, divide y, multiply dx, right? So I've got dy over y equals dx over x. Is that cool? Okay. Why is it nice that I can do that? Because what can I do to both sides now? Integrate. So what do you get here?
ln absolute value of
Kick
y
gas.
equals ln absolute value of x plus c.
Plus C. Okay. So that's basically a 180 problem. You guys agree? It's sort of like, shoot, I forgot the name of it. Screw it. It's that integration you'll learn a little bit later, where it's like natural log integration kind of stuff, or differentiation, where you have to bring it back in. So that's basically a 180 problem. Okay, that's fine. How do I solve for y? What do I do? Yeah, so I just raise e to both sides, right? So I get absolute value of y equals, and just to remind you guys, this is e to the natural log of x, e to the c, is that cool? Because I add powers when I multiply x, like bases. So then I get y equals, what's e to the c? Constant. And what's e to the natural log of x? Absolute value. Absolute value of x. You guys all with me? Okay. That is basically straight line, right? Actually, just yeah. Okay, let's do that. Now, let me give us some. Oh yeah, it's over there. Initial conditions. By the way, real quick, what does? Yeah. Okay. Good. Blah 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 blah. Good. What does the? What are the two checks for existence uniqueness? What's f of x y in that problem? F of x y. Y over x. Kick ass. Where is y over x continuous? Everywhere except around 0. So it's in every interval x not equal to 0, right? Every interval not including x equals 0. Is everybody with me? What's the partial with respect to y? Same thing, right? Okay, let me stop for a minute. So, when does that shit come into play? If I give us an initial condition, and let me just simplify this a bit, just to get to the point there, right? Just take the absolute out for a minute. If I give us an initial condition in common of y of 2 equals 3. You with me? Okay. Is this point in an interval that contains 0 necessarily? Could I make an interval around this that would not contain 0? Yes, so one interval of definition could be, for example, the biggest one I can make would be 0 to infinity. You guys all with me? Let me stop for a minute. Nothing major here yet, right? Where is the issue? Which value has an issue? X equals 0. So does this happen at 0? No. Can you make an interval that does not include 0 that's around 2? Yeah, all day. 0 to 3 would work also, for example. But 0 to infinity is the biggest. And of course, what would C be in this case? How do you figure out what C is? Output of 3 when the input's 2, so C is you can do it, Jeff, 3/2. So then I get this line. And then, of course, this line exists where? Now, real quick, if I did the absolute value of x, the reason that I could take that off is because I could have picked negative infinity to 0, and that would have been like the other side of things. Are you guys kind of with me? Okay, good. So, the existence uniqueness, remember, it's all about a region around blah, blah, blah that includes the initial condition. So the only time that it really could have issues is dependent on what initial condition they give me. So what if instead the initial condition was y of, which one did I want to do? Yeah, 0 equals 2. Is that going to possibly be freaky? Yes. You guys agree with me? Okay. And real quick, the answers, every single answer goes through what point? What point does every single answer go through? do it. Y equals cx. What point does it go through?
0, 0.
0, 0. Kick ass. All right, let me stop for a minute. So if my initial condition is y 0 equals 2, what happens when you try to solve that? So you get y equals cx. I want the output to be 2 when the input is 0. What do I get for c? What do I get for c?
2 over 0.
2 over 0. So does any constant work? No. Why does this not work? Do y'all agree with me that every solution goes through 0, 0? Yes. So the solution to this would have to go through 0, 0 and 0, 2. Could I write this in the form y equals cx? No. What's the equation for this? X equals 0. I like it. Maybe. So in this case, no solution exists. No solution exists for this. Okay. What if the initial condition was instead y of 0 equals 0? Let's try to solve for c. 0 equals c times 0. What does c have to be a single thing? It could be anything. How many solutions do you get then? Infinite numbers. Okay. Existence, uniqueness. If it's not, if it's violated, if one of those two or both are violated, I could have many answers. I could have no answer. When do I have which depends on what the initial condition there is. Initial condition was. Okay, maybe. Okay, enough of that. Okay. So, resolve this. You guys ready? Oh. Good, okay. So let's finally do this. I think what really is unfortunate for me is, real quick little side story. We chose schedules for next semester and I just ended up not getting 285, which kind of sucks. Because I don't know if I told you guys this, but it's been 7 years since I taught 285, which is always neat for a teacher. So right now I'm thinking of things I would do differently, and I'm like, well, I don't know when I'm going to teach it again, damn it. And one thing I might do differently if I ever teach it again is to start in chapter 2 and then go back to chapter 1 in the middle of chapter 2, sort of. Because it would just give us concrete things to hang some of this stuff on. Okay. This would be a beautiful place to start this course. Let me just show you. If I have this, tell me anything about that you can.
First order.
First order? Linear. ODE. Kick ass. Okay. Beautiful. Those are some of the best ones ever. Is this separable? Just as a side note. If it is, please separate it.
Oh, because you have to.
You guys see how it's not separable? Okay. That sucks. You always pray for separable because the only way that could be gross is if you get some weird integral when you separate the... But fundamentally, compared to other forms of differential equation solving, separable leads to the easiest situations. Just straight up integrate. Now, we all know some integrals can get gross. Can some integrals have series solutions, for example? Oh, shit. Okay. All right. Not a ton. Okay. What does this represent for the function? This is the function, right? What does this represent for the function, of course?
Sure.
The first derivative, which is also called the rate of change, which is also called the slope. Okay, good. Notice what this is then. This is a slope function. So here's where things get really nifty. And I will tell you this right now. I'm not going to make you do this by hand a lot. Very little, because this can get really freaky quick. What I want you to realize is, what inputs could I put in to determine a slope? What would an input look like? If I just want to look at this drawing, I'm not going to solve it. Do you see how by itself it deserves to exist? It is a description of the slope at every point, correct? So I could ask questions like, you guys kind of with me? And a side note, by the way, I think I said this the first day, but if you integrate something, why do you put plus c? Because I don't know where the answer is. I know what the shape is. If you tell me the derivative, I know what the shape is. I just don't know where it is. The thing with differential equations, do you notice how now I'm going x and y? So now I don't know where the answer is. Not just I don't know where the answer is, but I don't know where the answer is. It could be any xy point. I have to give an initial condition to know where it kind of lives. You guys semi with me? So watch this. For example, so slope, oops, let's do this. xy slope. So if I put 0, 0, what do I get? Holy shit. If I put 1, 0, 1. Neat. If I put, what else?
Wait, that would be negative 1.
Oh yeah, 1, 0, negative 1. Thank you. If I put 0, 1, that was my whole point, Joe. 1. Okay. You with me? If I put, you could keep going. Do you understand? How many, of course, you could do this for the rest of time. Go a little crazy, right? How do I graph what we've done? I don't know. Let's do a couple more. So like 2, 1. What would that be? What slope would that be?
Negative 1.
1 minus 2? That's negative 1 also, right? What about 1, 2?
1.
1, okay, right? 3, 1. 1 minus 3, negative 2. Yeah, okay, you guys kind of get the idea? Well, that's nice, Jeff, right? Yay. So if the initial condition was 3, 1, the slope at 3, 1 would be negative 2. Whatever that function will look like, whatever the answer looks like, it better go negative 2. It better go slope of negative 2 through 3, 1. You guys follow? Okay. So watch this. You'll quickly see why we don't make you do this by hand a lot. I want to, for every point, I'm going to graph a lineal element. What the shit, Jeff? Let me show you what I mean. So like at 0, 0, it's flat, correct? 0, 1. What's the slope at 0, 1?
1.
0, 1, it's 1, yes? Right? Isn't that a 45-degree angle? At least as good as I can do as a human? Okay. What would it be at, I didn't put it up here, let's just see, 0, 2, what would it be? That's crazy. So 0, 2 would be 2, is that cool? So then it would be steeper. 0, 3.
3.
Steeper? Yeah, okay. Do you see how it gets really difficult to graph by hand? Because the difference between a slope of 3 and a slope of 7, visually, it's really hard to show. Are you guys kind of with me? All right, now I can keep going. Do we do 1, 0? Yes. What's 1, 0? Negative 1. What would 2, 0 be? 2, 0 would be negative 2. Right? 1, 1. Did I do that? Did I do 1, 1? No. 1, 1 would be 0. Cool. In fact, what's interesting about this entire y equals x kind of piece? If y equals x, the slope is 0. So I can actually, I know this. All right, so this is difficult to follow. Can you see how disgusting it would be to have to do like 6 of these? I mean, just doing 1 would understandably drive you insane, right? Everybody would have a little less hair at the end of the semester. So thankfully, 2 things. I'll very often give you a completed one and ask you questions. Also, I'm going to show you a way to make a computer do this for you, right? I found several, I don't know, I'm just going to show you one I found. I can graph these. This is, remarkably enough, this is called a direction field. I don't know if anybody's ever heard of a vector field. So for example, the day of the tornado, I looked up the wind map, because I'm not the tornado, I don't know if anything actually touched down. But I looked at the wind map to see if I could see any vortices. So you guys know about wind maps? And if you look, it is actually a vector. Vector is the length that means stronger wind in that case, right? And then it also shows me the direction. So I can kind of see how the wind is flowing. If there's a tornado, you would expect to see kind of long lines going in this big circle. And you're like, oh, okay, don't go there. You guys are kind of with me. Okay. So let me do this. What order do I want to do this in? Bum, bum, bum. Yeah, let's show you this. Okay. I've got a little handout, but let me give you this handout. Let's do that first. Anytime.
Okay.
Anytime.
You get cast through your head. Yeah. So I thought a year ago. Nice. Oh, sorry. That's when you took it home. Did you don't get
Almost died.
That's so neat.
Yeah. It's just tedious.
All right, guys, so let's see. I'll never figure these lights out. I can't make you do what I want you to do. Damn it. Screw it. All right, sure. Can you guys see that okay? I don't know. You got your own copy. This is a completed direction field for that differential equation. Now, here's something we could do. Depending on the initial condition, that will determine what the overall shape is. But I completely have the shape of this sucker defined, correct? I just need a point to start. And this is just like 180, except 180 only really cared about sort of one direction. Here we've got slopes determined by both points, both coordinates. So what if the initial condition was, what, Jeff? Here, let me just be drunk for a minute. There we go. What if the initial condition was -2, 3? I don't really have a scale here. I sort of do. I don't know if you can see the scale there. Let's just say, do I have better ones in the back? Not really. Too bad. So I would be back here, -2, up here somewhere, right? You guys kind of with me? I think I do have a scale. I just can't really see it too well. Yeah. So -2, I think, is there. 3, I think, is there.
Yes.
Yeah. Thank you, guys. Okay. So there I am. Can you sketch out the solution? Where do I go from here in this direction? Follow the wind, right? When I go up, and then back here I would go down. Are you with me? So that would at least be one piece of the solution. Damn it. You guys kind of with me? What if instead, so that is 1. What if instead the initial condition was, what do you got, Jeff? I don't know, Jeff. Let's say -1, -2. -1, -2. So like right here. That would look like, oh, that's really freaky. Let me see. I think I did this correctly.
Yeah.
Roughly. It looks something like that. I'm trying to follow the arrows. Of course, I'm being vision challenged. You guys kind of get the idea?
Yeah.
Do you notice how this direction field is dependent on both x and y? Right? Amazing. What is different about example 2? It's only dependent on y. So can anyone identify something about this picture that I can maybe shortcut some of the work I have to do? For every x, what does it look like for every x above and below it? Is it different as they move along? For a given x, isn't it exactly the same slopes above and below it? Of course it is. Because the slope doesn't give a shit what x is. Do you guys understand what I'm saying? Couldn't I instead, I don't know what I look like right now, it doesn't matter. I just like being able to see it straight. Couldn't I instead just draw a single dimension? Y. That would capture everything. You guys understand what I'm saying? Do I need all of this? Do I need every value of x to capture the idea of this? Of course not, because I keep freaking repeating the same shit, right? You guys kind of follow? Okay? So instead of making a full direction field, which just has extra information, I could instead make something called, you're going to love this, it's called a phase portrait. Yay, Jeff. The name is silly. Phase portrait. It's like I'm asking you to phase in and out of existence, and then I'll paint you. All right, that was a joke just for me. So, really quickly, help me out. This is interesting. Let me do a couple examples of initial conditions. If the initial condition was, what do you got, Jeff? It doesn't matter. 0, 3. Where's the scale on this thing? I really can't see. 1, 2, 3. Is that right? I think so. Okay. So 0, 3. Can you see what the shape would look like? It's kind of going down and then over. Do you see how right at this point right here, do you see how it's flat? Okay. And then it goes up. What does that look like? Okay, it's an asymptote there, but generally the shape kind of looks like an exponential, right? Okay. You guys all kind of with me? Okay. What if the initial, so that's 1. What if the initial condition instead was -1, what do you got, Jeff? 1. -1, 1. If I'm born on that line, okay, that's weird, I don't care. If I'm born on that line, do I ever get off of that line? Do you see what I mean? Nope, I'm stuck on the damn thing. If I don't start on this line, do you guys all see, and somebody just said it earlier, if I don't start on this line, I can actually never get there. That's freaky. Now, of course, y is 1. What else is a flat condition? 0. And of course, looking at the equation, why is that true? Because what can you do with the equation? Factor it, and you can see where it equals 0, correct? And then you can see where these weird, if you're not born here, you can't be here, right? Or like a friend of mine from Maine used to say, if you can't get there from here, so if you're not there already, you ain't never going to get there. Does that make sense? I know I speak very technical language. If you're born on the line, you stay on the line. Okay. None of this is perfect. You're born on the line. Sorry. I'm not happy if it's born on the line. All right. So if I factor this, of course, what do we get? Factor this. Y squared times 1 minus 1. Okay, so the critical points would be 0 and 1. That correlates to where the flat lines are, correct? Okay, so here is what the phase portrait would look like as soon as I find blank paper. There we go. Whatever that is, it is now mine. Okay. So let me write this down again. I don't know, can you see that? Okay. Oh, I hate overhead stuff. Okay. The critical points, 0. Yeah, y equals 0, y equals 1. If I just look at the one dimension, because that's all I need, because it's just going to repeat it forever in both directions, because it doesn't care what x is. I can plot my critical points. So that's where it's flat. Above 1, will it be going up or down? How do you tell? If I put a number bigger than 1 into the thing that tells me what the slope is, what do I get? It's going down, correct? And in fact, looking back at the... Isn't everything above 1 going down? Yeah. Yeah, okay. So this will be down. That's much better than an entire direction field. I only need an entire direction field if my slope is dependent on y and x. Does that make sense? I don't need all that shit if it's just going to repeat. This is much better. What about between 0 and 1? Give me a number between 0 and 1. 0.5. I love it. So isn't that positive and that's positive? So it's going up between 0 and 1. And of course, what about below 0? Give me a number between, but it's below 0. This is squared, so it's positive. 1 minus a negative is positive. Going up. And look back at the picture. Are they going up? Yep. All right. We call this, I'm just going to tell you what we call it and see what you guys, if you agree with the word. We call that an attractor. The critical point of 1 is an attractor. If my initial point is in here or up there, my function wants to go to it. Do you guys see that? Isn't that a great name? Math people, we're not great at naming things. Have you noticed that? A lot of times. Sometimes we get it right. I don't know if you get it. Okay. I don't know if you agree. So that's an attractor. As an O or an I. Now, if I had one that was like this, just to show you an example, if I had one that was like this, what do you think I'd call that? Instead of attracting, I am repelling. Yes, Jeff, you are repellent. I think that's repel or, I don't know how to spell shit. Okay. This guy, is it an attractor or a repeller? Is 0 attracting or repelling? No. We call this semi-stable. Which sounds like a perfect word to describe, at least me as far as I know. Some of you guys might be able to relate to that. I'm semi-stable. That's going to be my new way of saying, how you going, Jeff? I'm semi-stable. Does that kind of make sense? That name? It's not an attractor or repeller. So what I would call this, I would call it a tractor. I could also call it stable. And a repeller, I could also call it unstable. It's trying to get away from something instead of trying to come towards something. Okay. But attractor, repeller make more sense than stable, unstable, to be honest. Okay. How are we doing out there? Okay. So the whole idea, why we call it stable, is because if I start near it, I am definitely going to go towards it. If I start near a repeller, I go away. I just go crazy, out of bounds, go to infinity. I'm unstable then. That's one way. That's why they called it that. All right. That's not too bad, right? Now, real quick. When I learned this, I wasn't shown enough to understand what the shit that even really means, right? So some of you guys might be like, is that easy? I don't care what dy dx they give you, as long as it's based on y. Can you all make that? That's relatively easy. Do you agree with me, or am I insane? Okay. Well, both can be tried. So let phase portraits be simple. The trick now is, what the hell does that mean for the solution of something, correct? So here, let me give you an example, a concrete example. That would be awesome, Jeff. Let me see, where did I put it? There it is. Blah, 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 blah. Let me make sure I didn't forget anybody. Yeah, okay. All right, let me do this first, before I do that. This kind of is a baby step in the direction of figuring out what this means for us. All right, so very quickly. Could you guys take a minute? Let me see. Let me really throw this one at you. Why not? Oh, let me do this. Let me make it real. Okay. Okay, help me out. Critical points. Right? Now this is exciting because there's no numbers, but we're in freaking differential equation. We're cool then. What's one critical point?
0.
Equals 0. What's the other critical point? Say again? A over B. I love it. Just make each one 0, correct? can you take a moment and create a face portrait, please? Let's see, what can I tell you about A and B? Let's assume A and B are both greater than 0. That'll make this easier. Is that cool? Assume A and B are both greater than 0. All right. Otherwise, there's a lot of uncertainty here. So assume A and B are both bigger than 0. So if I put something less than 0 in, that would mean that this would be negative, right? And this would be, if I put something negative in for P, won't this term become positive? Yeah. Positive plus positive is positive, so this would be down. Is that cool? Okay. What about above A over B? This would be positive. What would this be?
Negative.
Negative. I love it. So this would be down. What about in between those two? Like it's a little weird. So what if I put like A over 2B in? You with me? Okay, so that would be positive. So let me just write this again. That would be positive. That's all I care about is the sign. And then I would get A minus B times A over 2B. You guys kind of with me? So this would be A minus, bam, bam, half of A. That's positive. That's all I care about. Positive times positive, positive. Okay. A over B, you would call it what kind of critical point? Is it an attractor or a repeller? Attractor. This is an attractor. Oh, I don't want to write that there. I don't want to. A over B is an attractor. And of course, 0 would be what? Repeller. All right, let me stop for a minute. So I can actually sketch rough sketches of solutions given some certain initial condition. So if the initial condition had me up here, what would it look like? It would have to always be going down, but what happens right here, this would be flat, so I could do this for myself. Those are flat, right? So can you imagine what this must look like, the shape of this? Yeah, like this. I love it. What about over here, of course, on this side is 0? What has to happen? This is flat, and this is down, so it's going to have to start close to this, and then it's going to go down. So the slope is always down. Are you guys with me? What about in the middle? This is flat. This is flat. It would look like that in the middle, correct? Now, obviously, I want you to understand, the answer can't be all three because then it wouldn't be a freaking function. But depending on the initial condition, it'll tell me which region I live in. Does that make sense? So I want to show you a concrete freaking example of this, right? Okay. So I'm going to kind of skip, I kind of want to talk about the work a little bit. So watch this. Everybody got what they want from this? You guys kind of with me? Okay, so let me make this really, really, really concrete for you, okay? Because I understand, as a student, you're like, please, your God. Less theory, dear God. Real quick, what if I had this equation here? I hate overheads. Why am I on it? I don't know. What do I want to use? Sure. To kind of cut to the chase, real quick, is that separable? Is it separable? Shit, yes. Right? Couldn't I just divide by y minus 2 and then multiply by dx, right? Is that separable? Yes. And real quick, before I forget, I'm going to forget this, but any differential equation, first order linear differential, not linear, first order ODE, that's only a function of y, they are called autonomous. And one reason we call it autonomous, what does it mean to have autonomy? Yeah, operates by itself. So its slope the slope of y is dependent on y. So it controls itself. So it kind of makes sense. Again, we're doing good. Several words in a row that make sense. So we call these autonomous because the function y controls itself. It controls its own slope. Does that make sense? All right, I like it. Just to cut to the chase, if I do divide by that, and then I integrate, is everybody with me? Right? Here, I'll do half the problem. Okay. Oof. Oh no. So anyways, caught on. I did half the problem, right? How would you do this? We're not going to do it right now, but what method would you have to use to integrate this? Everybody's favorite. What is it? No?
Partial fraction.
Not U sub, no.
Is it partial?
Partial fractions.
Yeah, baby.
Right? Remember a over y plus b over y minus 2 equals 1 over y and y minus 2. Blah, 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 blah. You guys all with me? Could that happen this semester, that you actually have to do it?
Yeah.
Oh, shit, yeah. So if I remember, I could put up in the Canvas, if somebody reminds you, my little sheet going over how partial fractions works, in case anybody needs a refresher, right? And we'll do a problem like this, just not right now. We'll do it later. I've got it worked out. Blar. Okay. So eventually you get to, let me see, where do I want, screw it. At the very end, blah, 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 and you solve for y, you get here. Believe it or not. That is the solution to this. And real quick, what's the existence uniqueness theorem say? What's f of xy? This. Is it continuous everywhere? What about its partial? Don't even do it. Is it continuous everywhere? It's partial. Hell yeah. So there exists a unique solution for any given initial condition. Are you guys? That's what that means. Are you with me? Okay. So for every single any initial condition I give you, this is an easy question. What changes for each initial condition that changes? What changes? If I give you an initial condition, what changes here? C. Okay, good. So C, of course, every initial condition, I plug the shit in, I figure out what C is. Are you guys kind of with me? Okay. Real quick also, before I forget, somebody's favorite thing, what is the trivial solution to this? This is very interesting. How many trivial solutions are there? Or let me say this differently. How many constant solutions are there? 2. What are they?
0, 2.
You with me? Okay. Very quickly, let's do this. Those are basically the critical points, right? So do you see how this makes sense? Sometimes differential equations, let me ask you this. Is there any way in the world that I can make a constant that'll give me a 0 answer here? Do you guys agree?
Yeah.
There's no way to make this 0, because the only way to make a fraction 0 is if the top is 0, and the top is always freaking 2. So do you see how that is not, you can't access y equals 0 with this family? What about y equals 2? What would C be? If C is 0, do you guys agree that this is y equals 2? Okay, so you can access that one through this family. Do you understand what I'm saying? Okay. Oh, shit. Oh, man. I got to set up something real quick. How do I do it? I don't know. There. Yes, okay, thank God. I'm going to use Desmos, one of my favorite things in the world. Oh, yeah, I also want to use that. Look drunk for a little bit. All right, so what I want to do, also, can you guys take a minute and do the face portrait for this? Damn, it's already 10:30. Shit. Time flies. Okay, we set this up while you guys do that. Oh, two. All right, let me catch up to you. So, If y is bigger than 2, both of these are positive, so it's up. If y is less than 0, both of these are negative, so that's up. Is that good? And if y is between 0 and 2, this is positive, but this is negative, so that's down. Okay, so I could do this, this, and this. Is that cool? Sorry. Just rough sketches, correct? I don't know if you guys remember doing like the first derivative test, you do the thing, and then you can do a rough sketch from a million years ago. Okay. So, what I have done, just to make this really concrete, everybody's got that kind of sketched out, just so you can see this while I'm doing this. So let me switch over to this dude. So I have put in there something really cool you can do with Desmos. Let's see, I forget this. Oh, thank the gods. Is I put in there that, and anytime you put in like ABC or whatever, it allows you to put a slider. I'm almost certain most of you guys have played with that. If you haven't, that kicks so much ass. Of course, what's changing C again is the choice of initial condition, right? You guys with me? Okay. So don't forget, look at your phase portrait. Does it match up with that solution? Now, of course, that solution exists in two different parts, correct? So the solution to the differential equation, so my initial condition, could my initial condition exist on both of those? Let me say this again. The initial condition is a what? A point, 1 point. Could it exist on both of these? No. So if the initial condition was there, it can also be there. You guys with me? So the big thing about the interval of definition is either this interval or that interval. How do I know which one? Well, what's your initial condition, right? So mathematically, this is the full picture. Solving an initial value problem, that's the answer, or that's the answer. It depends on where your initial condition was. Are you guys all with me? Kicking the ass. And of course, the initial condition they give me gives me what C is. In this case, whatever they were, they made C1. Now watch what happens. Watch what happens. If I go this way, it's not very interesting. This is kind of like the idea of why I can do a phase portrait. Isn't it just moving left and right? The shape doesn't really care what x is necessarily, right? All right, because the shape is the same. I'm changing the x and the shape is the same. Same shape, right? Now watch what happens when I go to negative c. In fact, watch what happens when I go... What happens at c equals 0 again? I get 2, yes? There it is, right? And now what's going to happen when I get C negative? What's the one region we haven't accessed yet? The middle. Isn't that neat? And that matches with the little stupid sketch we made, correct? That's the connection. That's the concrete connection between phase portrait shit and the little sketch and the actual solutions. Now this one, what would the interval of definition be for this if the initial condition was in here? Yeah, everything. I love it. You guys kind of with me a little bit? Okay. That's kind of cool. Yes? Also, let me show you this while I got whenever I use the computer, I've got to look drunk. All right, here is something nifty. If I remember, I'm going to put it up in Canvas. Have any of you ever seen GeoGebra? GeoGebra. All right, it's really kind of nifty. I know, real quick side note. If you haven't taken, wait, it's not that, it's plot.ninja. If you haven't taken Calc 3 yet, oh, did I spell that right? Does it no longer exist? Plot dot, oh no, don't tell me it no longer exists. Oh, that sucks. Calc 3, yeah. Oh, Calc Plot 3D, that'll work too. But this sucks, because one of my former students in Calc 3 made plot.ninja, and it was one where you could plot something in 3D and it could show you contour curves and all that kind of stuff. It was so cool. But I think Calc Plot 3D is pretty good. Okay, sorry. It makes me a little sad. I have to reach out to him and say, hey man, what happened? Okay, this guy. Coming back to this guy. Let's put in here, oops, y prime. So what was y prime for this guy? It was y times y minus 2. Show direction field. Okay, come on. Come on, right? Dear God, I'm not going to make you do this by hand. Yeah, you're welcome. So, let's see. Let's put in here 2. And then test solution. Okay, see, that lines up, correct? So this is kind of cool. You could actually put in what you think a solution could be. So another solution would be, what was it? 2 over 1 minus e to the 2, and the input's t here. Let's see if it's able to handle this. Well, I probably got to put this in parentheses. Become a whole thing. There you go. Let's see. There. Okay. Sweet. Look at that. Does it line up with the direction field elements? Do you see that? That's cool. Now, the immediate good thing about this website is you can plot a direction field, because that's the one you don't want to do. But the nifty thing is you can also plot what you believe a solution is, and you can very quickly tell if it's bullshit. So if I just put in here t squared, all right, that completely goes against. So that's a quick, try again. Are you guys kind of with me? So if somebody reminds me, because I am not going to remember, I could throw that link up in Canvas, because it's kind of a gross link. You guys can see it, but I can put it up in Canvas. If somebody please reminds me. If not, oh well, too bad. One less tool for you. Okay. Blah, 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 blah. Let's see. You want to talk about that? No, it's okay. All right, let me leave that there in case I want to come back to that. Yeah, beautiful. Oh yeah, cool. We did all that. All right. One thing that I do have to assume in order for these to work the way I want them to, so if I have a first order linear differential equation, one thing that must be true so this is a first order linear autonomous differential ODE. Good Lord. First order, doesn't have to be linear, my fault. First order autonomous ordinary differential equation, because this could have nonlinear elements of y. I have to have f and f prime, basically df dy, have to be continuous, and that's sort of like related to the uniqueness and existence theorem. Okay. So that's a little side note. Oh, cool, we did that already. Okay, so awesomeness. Okay, bam. Okay, beautiful. So let's talk about. So pretty cool with that. So that's section 2.1 is about direction fields, which you now can use that GeoGebra website to kind of graph the direction field stuff. I'd probably give you a problem. We have to do a little bit of that just to make sure I understand that you understand the concept of where the hell those linear elements come from. I'm pretty sure all of you do. But at the most, I would ask you to just do a couple, just to kind of show me. I'm not going to make you do a complete direction field, right? So let's finally delve into, so we got phase portraits in 2.1 that deal with autonomous differential equations. What does autonomous mean? What's it mean for a differential equation to be autonomous? If I had this differential equation here, this has to be a function of
P.
Okay, P. So that's autonomous. And that's why you can make a phase portrait for those. You can always sketch the rough sketch of what the things would look like in each region based on if it's an attractor, repeller, or semi-stable. You guys kind of with me? Okay. All right. Okay. So, we are finally in the section where you can actually solve stuff. Okay. You have to identify So the way I like to teach this is you try to rule out certain things. So if I give you a differential equation and I say solve this, you rule out separable. You don't immediately start trying to do some weird shit we're going to learn later. The first thing you look for is it the easiest kind of differential equation? If it isn't, then I'll think about something weird, right? So if I give you this, is that separable? And of course, separable means going to get all the y stuff on one side, all the x stuff on the other. All right, good. Solve it. Is it autonomous? Is it autonomous? Nope. So I couldn't do a face portrait. It would be a freaky ass whole direction field. Question? Yeah, let's go ahead and do that. Okay. All right, let me catch up to you guys a little bit. dy over y squared equals x dx. This side's nice. Be really careful. I'm pretty sure none of you guys are going to do this anymore. Maybe it's been beaten out of you, but it's not natural log of y squared, right? It's one of the banes of my existence. It's just like, oh, everything's natural log. No. The only power that I can't do using the power rule backwards is -1. Yeah. This is not -2. So what's the interval of this?
Negative y to negative y.
Yeah, -1 over 1.
Yeah.
Is that cool? Same thing as -y, negative y. How do we solve this for y? Y. Flip that side and then change the sign. So it'll be y equals -1 over stuff. Is that right? I love that. Is that right? Sometimes I do things too quickly. If you really wanted to, if I doubled the top and the bottom just to get rid of the fraction that's internal, what do I have to be careful about?
2y.
So we barely ever write 2c. I would just write some other, So normally in this class, very often in the early going, we will call that C1, and then as it adjusts, we'll call it C2. Isn't twice C1 a constant? Yeah. So I double top and bottom. Is that cool? Yeah. Some of you guys are still looking at me like I'm crazy. I just double top bottom because it's an internal fraction. I don't like for exception. I want, okay. Double top and bottom, twice C1 is still a constant. I'm not going to write 2C1, I'm just going to write C2. It's just another constant, right? You guys kind of with me? Right. That's nice, right? Yay. So, since this came up earlier, I figured why not? Let's do it. Let's do a partial fractions. So, I kind of gave the game away. Yeah, that looks yummy. Let's do this one. Be a good review. That one, is it separable? Yes. Is it autonomous?
Yeah.
Yes, good. Okay, but right now I just want you to solve it. So you identified it's separable. I know the method to solve it, right? So that's what's going to, the diff-q is basically that. What form is it in? Tells me what method to try. That's what I meant by linear is all blah, and diff-q is very bam, 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 very recipe-ish. If you see what form it's in, you know what method to try. So let's see who remembers how to do partial fraction decomposition. Yes. So how do I set up part fraction decomposition? Does anybody, what's the first step on this? So obviously I'm going to integrate, but I need to first break this up because I want to do the integral. I got to break it up. Yeah, I got 1 over y minus 5y plus 2 equals, what do I, and this is a really good example. I said this before. In this class, we will sometimes solve equations by assuming what the answer looks like. And we'll be able to do that based on kind of like what's happening in the equation. We're not always going to be able to do that. But that actually is how we develop methods. And I showed you some of those methods already. This is a beautiful first example of assuming what the hell the answer is going to look like. I know the answer being what the hell two fractions did this come from, will be something over this guy plus something over this guy. Right?
Yeah.
When does the top become like bx plus c? When this is an irreducible quadratic, right? What happens if this was squared, for example? I would have to have a plus c over y plus 2 squared, right? Okay, so you gotta remember all that stuff. Oh shit. This is a nice one. So now what's the next step? Sorry? What's the next step?
Multiply y plus 2.
Yeah, multiply both sides by the denominator.
Mm-hmm.
Okay. So this picks up y plus 2 and this picks up y minus 5. Is that cool? Right. Okay. That's a quick way to do that. Just he's going to pick up the one that this isn't. He's going to pick up the one that it isn't. Okay. There's two ways to kind of do this. I could solve the systems of equations. I much prefer to say if y equals -2, that kicks ass. Yes? If y equals -2, what's this? 1, because it doesn't give a shit about y. So it'd be 1 equals 0 plus -7b. Is that true? Yes, okay. Is that what it wanted to do? It doesn't matter, Jeff. It'll just be different from what you did. Yeah, that's good. Yes, okay. Everybody with me? So b is -1/7. If y equals 5, I get 1 equals 7a. So a is 1/7. Is that cool? So you don't have to do systems of equations always. Sometimes this doesn't work. But when it does, hell yeah. So what does that mean? This becomes the integral of we've just figured out what this shit is. So what is it? What's A? 1/7. So it'll be, can I just put a 1/7 out front? So it'll be 1 over y minus 5 minus, good, because b is negative, 1 over y plus 2. You guys all with me? Does that come back a little bit? And on this side, of course, I just get x plus c. So this would be 1/7. Good, 1/7. Gotcha. Natural log of y minus 5 minus natural log of y plus 2 equals x plus c. Everybody with me so far? Oh, this is so good, Jeff. Yay. What can I do in here? Yeah, so it'd be natural log of y minus 5 over y plus 2. Right? Can I solve this for y? I didn't say do you want to. I said can you? In theory. First thing I would do is multiply by 7.
Yeah.
Alright, so I get natural log. I should put C1 just to get you guys in the habit. And 7x plus C2. Then what can I do? Yeah, e to the stuff. So e, what happened? Are you guys at the point where you can just kind of See what's going to happen here?
Yeah.
If e to the 7x times e to the c2, so I get c3. And again, anytime I put something up here and you're like, where the hell did that come from? Ask. Okay. Either you all see it or nobody wants to ask. Okay. Can you solve that for y? What sucks? Is it y in two places?
Yeah.
Stupid y. So if I multiply both sides by y plus 2, I'll get this, correct? Oh man, this is so great, Jeff. Oh, I got more room in there. Sorry?
Can you repeat why you put C2?
Oh, here.
Yeah.
What did I do from this step to this step?
Multiply those by one.
What's 7 times C1? It's not C1 anymore, it's some other constant.
So the 7 just get absorbed in this C.
Absorbed. I love it. That's a constant. Times another constant is just a different constant. You guys all with me? And at the end, whatever form I put it in at the end, C1, C2, whatever the shit, doesn't matter. Whatever the C ends up being, I can determine it with any initial condition. I don't care what the C's were that went into it. It just matters that it is a constant at the end. Okay, I like it. Man, I'm always pushing my luck with you guys. Like, come on, Waller. Okay, real quick. I would subtract this the stuff that has y in it, get it all together. And I would add the 5, get the stuff without a y in it together. And then I can finally take a y out. Can I do two things? Take a y out and then divide by the shit?
Yeah.
Yes? So I get 5 plus 2 c3e to the 7x over 1 minus c3e to the 7x. Yum! Okay. That was creepy, Jeff. Too bad. Nifty? Do you understand how the hardest part about most separable equations will not be the integration? It will be the solving. I think some of you guys might agree with me now. Okay. Sometimes it'll be the integration. All right, guys, that's plenty. Actually, wait a minute. We desperately need a quiz. Quiz Tuesday. I'll just do section 1112. Is that all right? You want more?
So did we actually go over and done the 1.3, or was that just kind of that brief, like, 2
That was
sentences?
very brief.
Okay.
You guys have to try it and come with questions. That one problem is the one that's the worst. The rest of them are just adjustments to the examples.
I have no idea.
Put a lot of stress on the 1.3,
Wait, where do you go after?
1.3 is one of those, it kind of depends on where you go after this. So a lot of people are going to go into engineering, and then it's going to be very specific engineering application.
Wait, 1.3 is.
So, and some of you guys are going to go into bio.
Oh, he multiplied
physics or whatever,
each
or
side
science.
by
yeah, by
y
y
plus
plus
2.
So it really is just
And
saying,
then
hey, all
after
the
that, he moved all the stuff with y's as a coefficient on one side.
You back out and then